Hi, I'm Ian, and I, Jerry, John, Nikhil, and Rose have built musical chess, which you just saw in the user demo. So the architecture of our system, as in our original proposal, looked like this. There's a central game state that knows everything about the actual game of chess, and then that's sort of hooked up to all these other components, like the UI, the engine communication so you can play against the computer, serialization so you can load and save games, and of course sonification so that you can hear them. Our final project actually ended up following pretty much this structure. The main thing that changed here is the sonifiers as we figured out what we actually wanted and had time to implement. The central thing in that diagram is the game state. The game state is implemented as a succession of classes, each knowing more about the game. So the board just knows positional information, where are pieces on the board, what are squares. Game state adds to that things like whose turn is it, who can castle, if you can do en passant, and also contains logic for checking the legality of moves. Does this put me in check? We omit certain tournament rules related to stalemate. And then game takes game state and adds move history. Separate from all this, as Nikhil will tell you about, we have support for loading PGN files, and that interacts closely with game state.
So not much has really changed for the synthesis in terms of design since the midterm. We've added some functionality here and there, moved around some things behind the scenes, but the main API is pretty much the same. We have our two abstract-based classes, C Sound Processor and C Instrument, and these provide universal functionality for all the child classes. This includes things like setting the sample rate, the gain, pan, and also setting the parameters for an ADSR. And the main class we have generating values for sound is our C Wavetable Oscillator. So this reads values from a Juice Audio sample buffer reference. This is different in that we used to have a wavetable class, but we've since moved over to this method recently. And this is the main class, like I said, for generating values that will be producing sound. And let's move over to C Scheduler. So this allows you to organize C Instrument instances in time. You can use this for melody construction, chord construction, if you just want an instrument to occur at a later time. This is extensively used in our sonifiers, especially the story sonifier. And C Looper is the same as a scheduler. Just when it reaches the end of its contents, it returns to the beginning like you would expect a looper to do. C Main Processor is basically a wrapper for the main output buffer that we are expected to fill, that Juice expects us to fill. It provides functions such as just adding instruments to it, removing them. You can also schedule things just like a scheduler. It allows for easy manipulation of your instruments and creating sound. And all sonifiers have this as a member, and it's placed in the process function. And as I said, it wraps the main output buffer. And one notable thing to say from the midterm is we have switched over to smart pointers for most of our, when we want to dynamically create an instrument or something. Previously we had raw pointers. However, it was becoming a bit of a challenge to manage all the memory and make sure everything was working correctly. So we switched over to smart pointers.
For any sonification scheme, there are two important parts. One of them is onMove. It takes in the whole board by reference and sonify each piece on the board according to the scheme that the user chooses. And the other one is process. It spits out the next sample or the next block of samples whenever it gets called. Not a lot has changed since we last presented the debug sonifier, except for the fact that we're calling it the Zen sonifier this time. It produces drone-like sine wave sound so that it's the perfect sonifier when the users want to really think about the next move. It has a fixed set of frequency, gain, and onset values to choose from, and in this case, the position of the piece on the board are mapped to these values. So the rank of a piece is mapped to the gain, and the file of a piece is mapped to a frequency in the C major scale. We're also allowing a few instances of randomization, such as the panning effect.
Story sonifier, we first form a pitch to frequency 1-to-1 correspondence. For example, A4 is correspond to 440 Hz. And for each type of piece, we have an individual, unique melody and curve to represent. For white piece, we have sine wave, and black piece, we have saw wave. As moves are played and the game processes, layers are added to the background sound. For example, when you go one step, there will be a melody bass, which is low frequency, what happens, and then after the second step, what happens, the melody accompaniment. Then melody L and R will shows. The story sonifier also have a function that can change major key to minor key. And so the future potential will be like to change the key based on the game state.
We can even have non-musical sonifiers. So commentary sonifier just tells you what's happening in the game. For instance, knight b1 takes c3. It does this by stringing together pre-recorded audio clips, and it loads those audio clips from the executable itself, so they're bundled in just like the chess images that we're using, which simplifies deployment a bit. It uses the long algebraic notation. That way we don't have to determine whether or not the source square is ambiguous, and it can announce things like checks, promotions, captures, and outcomes like stalemate and checkmate. This demonstrates the flexibility of the Sonifier interface. It's not tied to any particular musical notion. It can just be any audio at all. And also this very pragmatic Sonifier could be used for things like accessibility. It can speak the move so you can still follow a game when you can't see it, and also pedagogy, so you can learn to visualize the board without looking at it. In the future, we'd be interested in extending this to actually commentate on the game, so saying, interesting move, or, oh, what a blunder, based on the engine evaluation, which could add a whole other dimension to this.
We've also written some sound effects that are intended to make our sonifiers more appealing. Each of these effects is its own class. We were able to pull in Juice's state variable filters and the reverb class. We also wrote the bit crusher effect consists of a downsampling effect and a quantization effect. Due to a tight time window, we have not yet integrated all of these effects with our sonifiers, but we do plan to use them in the future.
So for communicating with the engine, we really wanted to avoid implementing a chess engine. This is a big undertaking. There's open source engines that are really good, and that you could spend a whole semester on this and still not be close to beating them. But we still want the user to be able to play against the computer and for the computer to evaluate positions. So we just use an existing engine. And we can do that because engines talk over the standard protocol, the universal chess interface, which you just communicate with the engine over standard in and standard out. So here's an example with Stockfish. We can say, here's the position, evaluate it, come up with the best move. And this requires, for a chess interface, to spawn the engine as a child process, redirect standard in, standard out. And that's actually a bit tricky because that's easy to do on Unix systems like Linux, Mac OS, but there's no fork on Windows. It has this totally separate API for this. Luckily, we found the single header library that allowed us to do this without too much hassle. Now, for streaming live games from Lichess, fortunately, Lichess is also open source and has a really good API with nice documentation. And it has exactly the endpoint we want from this, where you make a long-running HTTP request, and it keeps sending moves as they happen. We can even do this in Juice, but unfortunately we found that you can't cancel the stream when you want to. There's a method for it, but it just doesn't work, at least not with all the backends. So right now we're just killing the thread. This is kind of gross, and in the future we would like instead to just do a polling approach where we repeatedly make requests to see if there are new moves. And we think this would work better within the constraints of sticking with Juice's networking API.
In this iteration of our application, we have also added support to parse PGN files. So PGN files are the standard convention used in the chess community to store and record chess games that have been played. The convention followed in recording these games is using the standard algebraic notation to depict moves on the board. These files also contain metadata about the game, such as the venue where the game was played and who were the players involved, etc. Here is an example of a sample PGN. As you can see, the tags are indicated by the square brackets, and the moves are indicated by the serial numbers. For example, serial number 1 indicates that the first move was played, and white played pawn to e4, and black responded with pawn to c5. The class structure of our PGN parsing class is something that inherits directly from the game state class. It primarily uses static functions to generate moves from the standard notation and executes them on the board. The reason we went with static functions is because we wanted to be able to use this outside of our normal games, as we would also want to have support to stream live games from Lichess. Since PGN is a computer-generated file, there is uniform convention followed, and we used regular expressions to parse these files. We tried using strings, but they didn't yield the kind of results we would have liked. So we went with regular expressions, and for any C++ 11 compiler should be able to compile this and run this without any issues.
So the UI underwent a pretty massive overhaul since the midterm. One of the back-end things that's quite fundamental to how everything works together is that we no longer use juice, action, or change broadcasters. Instead, we set Lambda functions for our app components, and they communicate through those. In terms of the interactive UI features, we made compartmentalized classes that handle the parameters available to the user. So we have something called player options, which handles whether the players are computers or humans. Sound options, which controls which sonifier is playing. Controls, which handles going forwards and moves, backwards and moves, stuff like that. This really allowed for streamlining and consolidation of our previous UI elements, made things much cleaner in both the front end and the back end. And a fun feature we were able to get working was dragging. We were quite excited when this came together. In terms of informational UI features, we were able to get a move counter working, text replaced with icons, and implemented square highlighting. So square highlighting is like showing possible moves for selected pieces, showing when your king is in check, stuff like that. Overall, the goal was to provide a familiar and easily digestible interface for the user, give the user a clear visual understanding of the tools they have and how to use them properly.
How do we know that any of these things we've been talking about actually work? So we validated initially just by throwing in some asserts. Since then, we brought in Catch 2, as we discussed during the midterm. And this was pretty easy. It's a single header library, so it's just an include and didn't require a lot of finagling with CMake. We've tried to build things in a modular way so that components can be tested separately. For instance, there's no need for game state to depend on synthesis, UI, or even anything juice. And that makes it a little bit easier to set up unit tests. We have unit tests for game state, synthesis, sonification, and PGN parsing. And then we also have some additional targets for testing manually, like terminal chess lets you just play chess in your terminal, or engine chess runs an engine, which is not convenient for unit testing. We also have stream test and sonifier test for similar reasons.